Hello and welcome to Nighttime Science. Tonight we are embarking on a journey through the cosmos, traveling across vast distances of space and backward through deep time. We will drift among planets and moons, through asteroid fields and icy realms, exploring the quiet majesty of our solar system, the celestial neighborhood we call home. There is no need to do anything now except to listen. Find a comfortable position, allow your breathing to become slow and regular, and let the gentle weight of relaxation settle upon you. As we begin our journey, imagine yourself floating in the darkness of space, surrounded by the soft glow of distant stars, watching as our story unfolds across billions of years. The birth of our cosmic neighborhood. Let us travel back in time now, far back to a moment long before the Earth existed, before any planet circled our sun, before there was anything but darkness and dust drifting through the void of space. This is where our story begins, some 4.6 billion years ago, in a region of our galaxy that was neither special nor remarkable. Just one small corner of the Milky Way where something extraordinary was about to unfold. In this ancient time, there existed what astronomers call a molecular cloud, an enormous collection of gas and dust particles floating through the cosmos. This cloud was vast beyond comprehension, stretching across light years of space, composed primarily of hydrogen, the simplest and most abundant element in the universe. Within this hydrogen were traces of heavier elements, atoms of carbon and oxygen, silicon and iron, all forged in the hearts of stars that had lived and died long before our solar system was even a possibility. Something disturbed this peaceful cloud. Perhaps a nearby star exploded in a supernova, sending shock waves rippling through space. Perhaps the cloud simply grew dense enough that its own gravity began to pull it inward. Whatever the cause, a process began that would take millions of years to complete. A slow and gentle collapse that would transform this diffuse cloud into the solar system we know today. As the cloud collapsed, it began to spin, slowly at first, then faster as it contracted, the way an ice skater spins faster when they pull their arms close to their body. This spinning cloud flattened into a disk, with most of the mass collecting at the center where gravity was strongest. The pressure and temperature at this central point increased steadily, atoms colliding more and more frequently, generating heat through friction and compression. In the heart of this spinning disk, the temperature rose to millions of degrees. The hydrogen atoms, stripped of their electrons by the intense heat, began to fuse together, combining to form helium and releasing tremendous amounts of energy in the process. This was the moment our sun was born, igniting like a cosmic lamp in the darkness, beginning a process of nuclear fusion that continues to this very day, some 4.6 billion years later. But the sun did not consume all the material in the collapsing cloud. Around it remained a disk of leftover gas and dust, a swirling accretion disk that would become the birthplace of planets. This disk was not uniform. Closer to the young sun, where temperatures were higher, only materials with high melting points could remain solid, compounds like metal and rock. Farther out, where the sun's heat was less intense, volatile materials like water, methane, and ammonia could freeze into solid ice particles. Within this disk, dust grains began to stick together. Collisions between particles, initially random and chaotic, gradually built larger and larger objects. A speck of dust might collide with another speck, the two adhering through static electricity and molecular forces. These combined specks would then encounter other particles, growing grain by grain, collision by collision. Over thousands and then millions of years, these accumulations grew from microscopic dust into pebbles, from pebbles into boulders, from boulders into mountain-sized objects called planetesimals. The process was not always gentle. Sometimes planetesimals collided and shattered, breaking apart into smaller fragments that would have to begin the accumulation process anew. But more often, especially as the objects grew larger and their gravity stronger. Collisions resulted in growth rather than destruction. A planetesimal with more mass would have stronger gravity, allowing it to attract and capture other objects more effectively. The rich got richer in this cosmic economy, with the largest planetesimals gradually sweeping up everything in their orbital paths. In the inner solar system, where only rock and metal could withstand the sun's heat, the planetesimals that formed were relatively small and dense. These would eventually become the terrestrial planets: Mercury, Venus, Earth, and Mars. Their growth was limited by the amount of solid material available in their hot environment, and so they remained relatively modest in size, dwarfed by what was forming farther from the sun. Beyond a certain distance from the sun, roughly where the asteroid belt lies today, temperatures dropped low enough for ice to form. Here, planetesimals could incorporate not just rock and metal, but also frozen water, frozen methane, frozen ammonia, and other icy compounds. Since these volatile materials were far more abundant than rock and metal, the planetesimals that formed in the outer solar system could grow much larger. These massive objects had strong enough gravity to capture even the hydrogen and helium gas that filled the disk, allowing them to grow into the gas giants: Jupiter, Saturn, Uranus, and Neptune. Jupiter formed first among the giants and grew to become by far the most massive planet, containing more mass than all the other planets combined. Its powerful gravity stirred up the asteroid belt region, preventing the material there from ever coalescing into a planet, and leaving instead a scattered band of rocky debris. Some planetesimals were flung inward toward the sun, others outward to the far reaches of the solar system, their orbits permanently altered by Jupiter's gravitational influence. The evidence for this ancient history lies all around us, written in the rocks and ice that have survived from the solar system's formation. Meteorites that fall to Earth today, fragments of asteroids that formed in those earliest times, contain microscopic grains that are older than the solar system itself, pre-solar grains from previous generations of stars. By studying the isotopes of elements in these meteorites, scientists can determine their age with remarkable precision, revealing that the oldest solid materials in the solar system formed 4.567 billion years ago, give or take a few million years. These ancient rocks also tell us about the conditions in the early solar system. Some meteorites contain chondrules, small spherical grains that melted and rapidly cooled in the heat of the young sun. Others contain calcium-aluminum-rich inclusions, the very first solids to condense from the cooling solar nebula. Each meteorite is a time capsule, preserving information about temperature, pressure, and composition from the era when planets were forming. The process of planet formation was not quick by human standards. From the initial collapse of the molecular cloud to the formation of planets large enough to clear their orbits took perhaps 100 million years. During this time, the solar system was a far more chaotic place than it is today. Planetesimals by the billions orbited the sun, colliding and merging, breaking apart and reforming. The inner planets experienced tremendous bombardment, their surfaces cratered and remelted repeatedly by impacts. Gradually, over tens of millions of years, the chaos subsided. The largest planets had swept up most of the material in their vicinity. The gas in the disk, no longer replenished by the collapsing molecular cloud, was either captured by planets or blown away by the solar wind, the stream of charged particles flowing outward from the sun. What remained was something approaching the orderly system of planets we see today, each in its own stable orbit, separated by vast distances of nearly empty space. But the young solar system was not quite finished with its violent youth. For several 100 million years after the planets formed, a period called the Late Heavy Bombardment brought a renewed surge of impacts as leftover planetesimals were scattered by gravitational interactions with the giant planets. The moon's heavily cratered surface bears witness to this era, its ancient highlands pockmarked by countless impacts from this turbulent time. Through all this violence and chaos, a pattern emerged. The four inner planets, small and rocky, orbited close to the sun where temperatures were high. Beyond them, separated by the asteroid belt, four giant planets orbited in the cooler outer reaches of the solar system. Still farther out beyond Neptune's orbit, countless small icy bodies populated what we now call the Kuiper belt, too distant and scattered to ever form into planets. This is the solar system that surrounds us today, a system born from a collapsing cloud of gas and dust, shaped by gravity and heat, collision and accumulation, chaos and order. Every planet, every moon, every asteroid and comet is a remnant of that ancient time, a survivor of the violent processes that transformed a diffuse molecular cloud into the intricate orbital dance we observe when we look up at the night sky. The story written in these worlds is a story of transformation, of simple materials becoming complex structures, of random collisions giving rise to predictable order, of a cosmos that began in darkness and cold and gave birth to light and warmth, and on at least one small blue planet, to life itself. Section 2. The Sun, our gentle stellar companion. Let us now turn our attention to the center of our solar system, to the great luminous sphere that makes all life on Earth possible, the star we call the Sun. It sits at the heart of everything, holding the planets in their orbits through the invisible force of gravity, bathing the inner worlds in light and warmth. The Sun is not a particularly large star by cosmic standards. In the vast catalog of stars scattered throughout our galaxy, it is classified as a yellow dwarf, a main sequence star of medium size and medium temperature. Yet to us, bound to our small rocky planet, the Sun is enormous beyond easy comprehension. Its diameter spans roughly 109 times that of Earth. If the Sun were hollow, you could fit more than 1 million Earths inside it. Its mass accounts for 99.86% of all the mass in the entire solar system, dwarfing even Jupiter, the largest planet. Deep within the Sun's core, at temperatures reaching 15 million degrees Celsius, hydrogen atoms fuse together to create helium, releasing energy in the form of light and heat. This process, called nuclear fusion, has continued without pause for the past 4.6 billion years and will continue for billions more. The energy generated in the core does not immediately escape. Instead, it takes a slow journey outward, passing through different layers of the Sun's interior, sometimes being absorbed and re-emitted countless times. A single photon of light generated in the core may take 100,000 years or more to reach the Sun's surface. But the Sun does not only emit light and heat. From its outer atmosphere, a region called the corona, there flows a constant stream of charged particles, electrons and protons torn from atoms by the intense heat. This stream is called the solar wind, and it flows outward in all directions, filling the solar system with a thin plasma that extends far beyond the orbits of the planets. The solar wind is not constant or uniform. Sometimes it flows slowly, moving at speeds around 300 kilometers per second, roughly 1 million kilometers per hour. At other times, particularly during solar storms or from regions called coronal holes, the solar wind accelerates to twice that speed or more, reaching 600 to 800 kilometers per second. These variations in speed create regions where fast-moving solar wind catches up with slower wind ahead of it, forming compression regions and shock waves that ripple through interplanetary space. The particles in the solar wind carry with them a magnetic field, an extension of the Sun's own magnetic field, dragged along by the moving plasma. This interplanetary magnetic field spirals outward from the Sun, forming what scientists call the Parker spiral, named after the physicist who first described its shape. The field lines, rooted in the rotating sun, sweep outward like water from a rotating sprinkler, creating a beautiful spiral pattern throughout the solar system. When the solar wind reaches Earth, traveling the distance of 150 million kilometers in about 4 to 5 days, it encounters our planet's own magnetic field. The interaction between the solar wind and Earth's magnetosphere creates a complex boundary region where the two magnetic fields push against each other. Most of the time, Earth's magnetic field deflects the solar wind around our planet, protecting the atmosphere and surface from the full force of this particle stream. But some solar wind particles find their way into Earth's upper atmosphere, particularly near the magnetic poles where the field lines dive down toward the surface. When these charged particles collide with atoms of oxygen and nitrogen in the atmosphere, they cause those atoms to glow, creating the beautiful curtains of light we call the aurora borealis in the northern hemisphere and the aurora australis in the southern hemisphere. Green light comes from oxygen atoms at lower altitudes, red light from oxygen at higher altitudes, and blue or purple from nitrogen. The corona, the source of the solar wind, is itself a mystery that has puzzled scientists for decades. The corona is the sun's outer atmosphere, a region of extremely hot but very thin plasma that extends millions of kilometers into space. What makes the corona strange is its temperature. The visible surface of the sun, called the photosphere, has a temperature of about 5,500 degrees Celsius. Yet the corona, farther from the sun's core and seemingly farther from the heat source, reaches temperatures of 1 to 3 million degrees Celsius or more. This seems to violate our everyday understanding of heat flow. Heat normally moves from hotter regions to cooler ones, yet here we have a situation where moving away from the heat source somehow increases temperature rather than decreasing it. The mechanism that heats the corona to such extreme temperatures remains an active area of research, though scientists believe it involves the sun's magnetic field, which can store and release energy in complex ways. The sun's magnetic field is not simple or uniform. It emerges from the interior in loops and arcs, creating regions of intense magnetic activity on the surface. Where these magnetic field lines break through the photosphere, they suppress the normal convection of hot gas from below, creating slightly cooler regions that appear darker against the bright surface. These are sunspots, areas where the magnetic field is particularly strong, sometimes thousands of times stronger than Earth's magnetic field. Sunspots come and go in cycles, waxing and waning over a period of approximately 11 years. At solar minimum, the sun may go for days or weeks with no sunspots at all, its surface relatively calm and uniform. At solar maximum, dozens of sunspots may dot the surface at any given time, and the sun becomes much more active, producing more solar flares and coronal mass ejections. These eruptions can send billions of tons of solar material hurtling into space at speeds of several million kilometers per hour. The light that reaches us from the sun takes just 8 minutes and 20 seconds to traverse the distance between the sun and Earth, traveling at the speed of light, 300,000 kilometers per second. This means that when you look at the sun, you are seeing it not as it is right now, but as it was 8 minutes ago. The sunlight warming your face on a bright afternoon began its journey from the sun's surface while you were still doing something else 8 minutes earlier. That sunlight, having taken perhaps 100,000 years to escape from the sun's interior, and then 8 minutes to cross space, carries with it energy that powers nearly everything on Earth. Plants capture it through photosynthesis, converting light energy into chemical energy stored in sugars and starches. Animals eat plants or eat other animals that eat plants, creating food chains that ultimately trace back to the sun's energy. The wind and weather, the ocean currents, and the water cycle all are driven by the uneven heating of Earth's surface by sunlight. Even fossil fuels, coal and oil and natural gas, are stored sunlight, the remains of ancient organisms that captured solar energy millions of years ago. The sun will not shine forever. Like all stars, it has a finite lifetime determined by the amount of fuel in its core. The sun has already consumed about half of its hydrogen fuel, and in roughly 5 billion years it will begin to run out. When that happens, the core will contract and heat up, while the outer layers will expand tremendously, transforming the sun into a red giant star that may swell large enough to engulf Mercury and Venus, possibly even Earth. But this is so far in the future that we need not concern ourselves with it tonight. For now and for billions of years to come, the sun will continue its steady burning, a reliable source of light and warmth for the planets that circle it. As we drift here in our imagination, watching the sun from a safe distance, we can appreciate it for what it truly is, not just a bright disk in our sky, but a massive nuclear furnace, a sphere of plasma held together by its own gravity, constantly converting matter into energy through fusion reactions in its core, sending light and particles streaming out into the solar system, creating the space weather that shapes the environments of all the planets. It is the anchor of our solar system, the dominant presence that defines the structure and dynamics of everything around it. Section 3. Mercury, the swift and peculiar. Let us now travel inward from the sun to visit the innermost planet, the small world of Mercury, orbiting closer to our star than any other planet. Mercury is a world of extremes and peculiarities, a place where a single day unfolds in a way unlike anywhere else in the solar system. Mercury is small, only slightly larger than Earth's moon, with a diameter of 4,879 kilometers. It is the smallest planet in the solar system, having claimed that distinction when Pluto was reclassified as a dwarf planet. Despite its small size, Mercury is remarkably dense, the second densest planet after Earth, indicating that it must have a large iron core taking up perhaps 60% of its total volume. The planet orbits the sun at an average distance of 58 million kilometers, less than 40% of Earth's distance from the sun. At this proximity, the sun appears more than twice as large in Mercury's sky as it does in ours, and the solar radiation is more than 6 times as intense. The sun's gravity is also much stronger here, accelerating Mercury to high speeds as it races around its elliptical orbit. Mercury completes one orbit around the sun in just 88 Earth days. This is Mercury's year, the time it takes to make one complete circuit from any point in its orbit back to that same point. But here is where Mercury becomes truly peculiar. While Mercury's year is 88 Earth days, Mercury's rotation period, the time it takes to spin once on its axis, is approximately 59 Earth days. This creates an unusual relationship between Mercury's day and its year. The planet rotates 3 times on its axis for every 2 orbits around the sun, a situation called a 3-to-2 spin-orbit resonance. This resonance is not random but is caused by Mercury's elliptical orbit and the tidal forces exerted by the sun. The sun's gravity has, over billions of years, gradually slowed Mercury's rotation and locked it into this stable pattern. The consequence of this 3-to-2 resonance is that Mercury's solar day, the time from one sunrise to the next sunrise as seen from the surface, is neither 88 Earth days nor 59 Earth days, but 176 Earth days. This is twice Mercury's orbital period. A single day-night cycle on Mercury lasts 2 Mercurian years. If you stood on Mercury's surface and watched the sun rise, you would have to wait 176 Earth days for it to rise again in the same location. The long solar day creates extreme temperature variations on Mercury's surface. On the side facing the sun, temperatures can soar to 430 degrees Celsius, hot enough to melt lead. This is not just because Mercury is close to the sun, but also because the long day gives the surface time to absorb heat continuously for 88 Earth days at a time. The sunlit side bakes under the relentless solar radiation, with no atmosphere to moderate the temperature or distribute the heat. But turn to the night side, the hemisphere shrouded in darkness, and conditions change dramatically. Without an atmosphere to retain heat, the surface cools rapidly. Temperatures on the night side plummet to -180 degrees Celsius. This is a temperature swing of more than 600 degrees, the largest of any planet in the solar system, a testament to Mercury's lack of atmosphere and its long, slow rotation. Mercury does have an extremely thin exosphere, too tenuous to be called a true atmosphere. This exosphere consists of atoms blown off the surface by the solar wind or kicked up by micrometeorite impacts. These atoms include hydrogen, helium, oxygen, sodium, calcium, and potassium. The exosphere is so thin that atoms rarely collide with each other. Instead, they follow ballistic trajectories, arcing above the surface before falling back down or escaping into space entirely. The total mass of Mercury's exosphere is less than 1,000 kilograms, far less than the air in a small room on Earth. From Mercury's surface, if you could stand there and survive, the sky would appear black even during the day, just as it does for astronauts on the Moon. With no atmosphere to scatter sunlight, the stars would be visible even with the sun above the horizon. The sun itself would appear enormous, more than twice the size it appears from Earth, and blindingly intense. But watching the sun move across Mercury's sky would reveal another peculiarity. Because of Mercury's elliptical orbit and its 3-to-2 spin-orbit resonance, the sun sometimes appears to move backward in the sky. At certain points in Mercury's orbit, particularly near perihelion when Mercury is closest to the sun and moving fastest, the planet's orbital motion temporarily overtakes its rotational motion. For observers at some locations on Mercury's surface, the sun would rise, climb partway up the sky, stop, reverse direction, and set again in the east where it rose, then rise again and resume its journey across the sky. This retrograde motion would appear as a brief loop in the sun's path. Mercury's surface is heavily cratered, bearing the scars of billions of years of meteorite impacts. With no atmosphere to burn up incoming objects and no geological activity to erase old craters, the surface preserves a record of impacts stretching back to the solar system's early history. The largest impact feature, called the Caloris Basin, spans 1,550 kilometers across, created when an asteroid perhaps 100 kilometers in diameter struck Mercury billions of years ago. The impact that created the Caloris Basin was so violent that it sent shock waves through the entire planet. On the opposite side of Mercury, directly across from the Caloris Basin, the surface shows unusual terrain called chaotic terrain or weird terrain, where the normal landscape has been disrupted and broken up. Scientists believe this was caused by seismic waves from the Caloris impact converging on the opposite side of the planet with enough force to fracture and jumble the surface. Despite its small size and proximity to the Sun, Mercury has a global magnetic field, albeit a weak one, only about 1% as strong as Earth's magnetic field. The existence of this field suggests that Mercury has a partially molten iron core, generating the magnetic field through a dynamo effect as the liquid metal circulates. This was a surprising discovery, as scientists expected Mercury's small size would have allowed its interior to cool and solidify completely long ago. Mercury is difficult to observe from Earth, always appearing close to the Sun in our sky, visible only briefly after sunset or before sunrise. This proximity to the Sun's glare also makes it challenging for spacecraft to visit. Only 2 missions have explored Mercury up close: Mariner 10, which made 3 flybys in 1974 and 1975, and Messenger, which orbited Mercury from 2011 to 2015, mapping the entire surface and studying the planet's composition and magnetic field. The images returned by these missions reveal a world that resembles our moon in many ways, but with its own unique characteristics. Mercury has vast, smooth plains possibly formed by ancient volcanic eruptions. It has enormous cliffs called scarps, hundreds of kilometers long and up to 3 kilometers high, formed when Mercury's interior cooled and contracted, causing the crust to buckle and fracture. And at Mercury's poles, in craters where sunlight never reaches, radar observations have detected what appear to be deposits of water ice, surviving in the permanent shadows despite Mercury's proximity to the Sun. As we leave Mercury behind, moving outward from this swift and peculiar world, we carry with us an appreciation for its strangeness, a planet where days last longer than years, where the sun can reverse its course across the sky, where one side bakes at temperatures hot enough to melt metal while the other freezes at hundreds of degrees below zero. It is a harsh world, airless and extreme, yet it holds its secrets still. Ice in shadowed craters, a magnetic field from a molten core, a 3-to-2 dance with the sun that has continued for billions of years and will continue for billions more. Section 4. Venus, the crushing beauty. Our journey continues outward now, leaving Mercury behind as we approach the second planet from the Sun, a world that shines brilliantly in Earth's sky, appearing as the morning star or evening star depending on its position in its orbit. This is Venus, named for the Roman goddess of love and beauty, a name that seems fitting given its bright and lovely appearance from Earth. But beneath its gleaming clouds lies one of the most hostile environments in the solar system. Venus is nearly Earth's twin in size, with a diameter of 12,104 kilometers, only about 650 kilometers smaller than Earth. Its mass is also similar to Earth's, about 82% of our planet's mass. For these reasons, Venus is sometimes called Earth's sister planet. But the similarities end with size and mass. In almost every other respect, Venus is a world utterly unlike our own. The most striking feature of Venus is its atmosphere, a thick blanket of gas that completely obscures the surface from view. This atmosphere is composed primarily of carbon dioxide, approximately 96%, with small amounts of nitrogen and trace quantities of other gases. The atmosphere is so dense, so massive, that the pressure at Venus's surface is 93 times greater than Earth's atmospheric pressure at sea level. To understand what this pressure means, imagine diving deep into Earth's oceans. As you descend, the weight of the water above you creates increasing pressure on your body. At a depth of 10 meters, the pressure has doubled compared to the surface. At 100 meters, it has increased tenfold. To experience pressure equal to that on Venus's surface, you would need to dive to a depth of nearly 1 kilometer beneath the ocean, almost 3,000 feet down. At such depths on Earth, only specially designed submersibles can survive. On Venus, this crushing pressure exists not in the depths of an ocean, but right at the surface, pressing down on every square centimeter of the planet. The temperature at Venus's surface is even more extreme than the pressure. The average temperature hovers around 467 degrees Celsius, or 872 degrees Fahrenheit. This is hot enough to melt lead, hot enough to make zinc run like water, hot enough that rocks on the surface would glow a dull red if you could see them through the thick atmosphere. Venus is hotter than Mercury despite being nearly twice as far from the Sun. This seems counterintuitive until you understand the greenhouse effect that traps heat in Venus's atmosphere. Sunlight penetrates Venus's cloud layers and reaches the surface, where it is absorbed and converted to heat. This heat radiates back upward as infrared radiation, but the thick carbon dioxide atmosphere absorbs this infrared light rather than allowing it to escape into space. The absorbed energy warms the atmosphere, which radiates some of it back down to the surface, warming it further. This creates a runaway greenhouse effect, with heat building up over time until the surface reaches its current scorching temperature. What makes Venus's heat even more remarkable is that it varies almost not at all across the planet. On Earth, the equator is much warmer than the poles, and the day side is warmer than the night side. But on Venus, the thick atmosphere circulates heat so efficiently that temperature remains nearly constant everywhere. The poles are just as hot as the equator. The night side is just as hot as the day side. Even the high mountain peaks, where the atmospheric pressure is somewhat lower, differ in temperature from the lowlands by only a few dozen degrees. Venus rotates very slowly on its axis, taking 243 Earth days to complete one rotation. Even more peculiarly, Venus rotates in the opposite direction from most other planets, spinning from east to west rather than west to east. This retrograde rotation means that on Venus, if you could see through the clouds, the sun would rise in the west and set in the east. The reason for this backward rotation remains uncertain. Some scientists believe Venus may have been struck by a large object early in its history, an impact powerful enough to flip its rotation. Others suggest that tidal effects from the sun combined with Venus's thick atmosphere may have gradually reversed its spin over billions of years. The combination of Venus's slow rotation and its orbital period creates an unusual day-night cycle. Venus takes 225 Earth days to orbit the sun. Combined with its 243-day rotation period, this means that one solar day on Venus from one sunrise to the next lasts 117 Earth days. But given the planet's perpetual cloud cover, sunrise and sunset are theoretical concepts on Venus. The surface exists in a dim, diffuse twilight with sunlight scattered by the clouds but never seeing the sun directly. The clouds that shroud Venus are not made of water vapor like Earth's clouds. Instead, they are composed primarily of sulfuric acid droplets. These clouds form in layers between 48 and 70 kilometers above the surface, creating a permanent overcast that reflects about 75% of the sunlight that strikes them back into space. This high reflectivity, called albedo, is why Venus appears so bright in Earth's sky despite its hostile surface conditions. Within these cloud layers, winds blow at tremendous speeds, circling the planet in just 4 Earth days despite the surface's slow rotation. These super-rotating winds, reaching speeds of up to 360 kilometers per hour, are one of Venus's many mysteries. The mechanism that drives these high-altitude winds to move so much faster than the planet rotates remains not fully understood, though scientists believe it involves the absorption and distribution of solar energy in the upper atmosphere. Below the clouds, in the dense lower atmosphere, winds are much slower, moving at only a few kilometers per hour at the surface. But the atmosphere is so dense that even these slow winds carry tremendous force. A breeze that would barely rustle leaves on Earth would exert hurricane force pressure on Venus simply because of the atmosphere's density. The surface of Venus, mapped by radar from orbiting spacecraft since visible light cannot penetrate the clouds, reveals a world dominated by volcanic features. Vast plains of hardened lava cover much of the planet. Thousands of volcanoes dot the landscape, ranging from small cones to enormous shield volcanoes hundreds of kilometers across. Some of these volcanoes may still be active, though confirming current volcanic activity on Venus has proven difficult. Among Venus's most distinctive features are structures called coronae, circular or oval features hundreds of kilometers in diameter, surrounded by ridges and grooves. Coronae appear to form where plumes of hot material rise from the interior, pushing up the crust and creating these distinctive patterns before the plume subsides and the surface settles back down. Venus has hundreds of coronaes, far more than any other planet. Venus also has mountain ranges and highland regions. The most prominent are Maxwell Montes, rising 11 kilometers above the average surface level, and the vast highland regions called Ishtar Terra and Aphrodite Terra, comparable in size to Earth's continents. But Venus has no plate tectonics like Earth. Its surface appears to be a single rigid shell, unbroken by the moving plates that characterize our planet's geology. Evidence suggests that Venus's entire surface may have been resurfaced by volcanic activity roughly 500 million years ago. The distribution of impact craters on Venus appears random rather than showing the accumulation patterns you would expect from billions of years of cratering. This suggests the surface is relatively young in geological terms, with older craters having been buried or erased by massive volcanic outflows. What triggered this global resurfacing event remains unknown, but it may have involved the buildup and catastrophic release of heat from Venus's interior. Despite its hellish conditions, or perhaps because of them, Venus has long fascinated scientists. Understanding why Venus, so similar to Earth in size and composition, evolved such different surface conditions may help us understand Earth's climate and the factors that keep our planet habitable. Venus represents a cautionary tale of greenhouse effects taken to the extreme, showing what can happen when carbon dioxide accumulates in an atmosphere and traps heat without the moderating effects of water and life. Several spacecraft have visited Venus, including Soviet Venera landers that actually touched down on the surface in the 1970s and early 80s. These hardy probes survived the crushing pressure and scorching heat for only brief periods, from 23 minutes to just over 2 hours, before succumbing to the extreme conditions. During their short operational lives, they sent back the only photographs ever taken from Venus's surface, showing a dim landscape of flat rocks under an orange sky, illuminated by the diffuse sunlight filtering through the clouds. As we depart Venus, moving farther from the sun, we leave behind this world of extremes, a planet where atmospheric pressure could crush a submarine, where temperatures melt lead, where clouds of sulfuric acid race around the planet while the surface barely rotates beneath them. It is a reminder that planets, even those similar in size and composition, can follow radically different evolutionary paths, creating environments that challenge our imagination and expand our understanding of what worlds can be. Section 5. Earth and Moon, our island and its companion. We arrive now at the third planet from the Sun, the world that is our home, Earth. After visiting the scorching heat of Mercury and Venus, Earth appears as an oasis, a blue and white marble suspended in the darkness of space, the only known world in the universe where life exists. Earth orbits the Sun at an average distance of 150 million kilometers, a distance so frequently referenced in astronomy that it has its own name, 1 astronomical unit, or AU. This distance places Earth in what scientists call the habitable zone, the region around a star where temperatures allow liquid water to exist on a planet's surface. Water is essential for life as we know it, and Earth has water in abundance. About 71% of Earth's surface is covered by oceans, vast bodies of liquid water that give our planet its distinctive blue color when seen from space. These oceans contain approximately 1.3 billion cubic kilometers of water, with an average depth of about 3,800 meters. The oceans moderate Earth's temperature, absorbing heat during the day and releasing it at night, absorbing heat in summer and releasing it in winter, creating a more stable climate than would exist on a dry planet. Earth's atmosphere, unlike the carbon dioxide atmospheres of Venus and Mars, is composed primarily of nitrogen, about 78%, and oxygen, about 21%, with trace amounts of argon, carbon dioxide, and other gases. This oxygen-rich atmosphere is not Earth's natural state. Early in Earth's history, the atmosphere contained little or no free oxygen. The oxygen we breathe today was produced by living organisms, first by photosynthetic bacteria billions of years ago and later by plants, gradually transforming the atmosphere over millions of years. The presence of liquid water and an oxygen-rich atmosphere makes Earth unique among the planets, but another factor contributes significantly to Earth's habitability: the Moon. At 3,474 kilometers in diameter, the Moon is unusually large compared to its parent planet. Most moons in the solar system are tiny compared to the planets they orbit, but the Moon's diameter is more than 1/4 that of Earth, making the Earth-Moon system almost a double planet rather than a planet with a satellite. The Moon's origin has been a subject of scientific investigation for generations. Early hypotheses suggested the Moon might have formed separately and been captured by Earth's gravity, or that it split off from Earth while our planet was still molten and spinning rapidly. But these ideas failed to explain certain key observations about the Moon's composition and orbit. The currently accepted explanation is the giant impact hypothesis. According to this theory, early in Earth's history, roughly 4.5 billion years ago, our planet was struck by another planetary body about the size of Mars. This object, sometimes called Theia after a Greek goddess, collided with Earth in a glancing blow, not head-on, but at an angle. The impact was catastrophic beyond imagination. Both Earth and Theia were vaporized and liquefied by the collision. Material from both bodies was thrown into orbit around Earth, forming a disk of debris circling our planet. Over time, this debris coalesced, pulled together by gravity, forming the Moon. Computer simulations of this process show that the Moon could have formed remarkably quickly, perhaps within just a few years or decades after the impact. Evidence supporting the giant impact hypothesis comes from several sources. Moon rocks brought back by the Apollo astronauts show oxygen isotope ratios nearly identical to Earth's, suggesting the Moon and Earth formed from the same material or from thoroughly mixed material. The Moon has a much smaller iron core than Earth, consistent with the idea that it formed primarily from the mantles of Earth and Theia, rather than from their iron cores. And the Moon's orbit, tilted slightly relative to Earth's equator, matches what would be expected from a large oblique impact. The Moon orbits Earth at an average distance of 384,000 kilometers, taking 27.3 days to complete one orbit. This is also the time it takes the Moon to rotate once on its axis, a situation called synchronous rotation or tidal locking. Because the Moon's orbital period and rotation period match, the same hemisphere of the Moon always faces Earth. We never see the far side of the Moon from Earth's surface, though it has been extensively photographed by spacecraft. This tidal locking is not coincidental but results from the gravitational interaction between Earth and Moon. Early in its history, the Moon rotated faster, but Earth's gravity created tidal bulges in the Moon's body. Friction from these bulges gradually slowed the Moon's rotation until it became locked with one face perpetually toward Earth. Earth experiences the same tidal forces from the Moon, creating the familiar ocean tides, and these forces are slowly increasing the length of Earth's day and pushing the Moon gradually farther away, though these changes are imperceptibly slow on human timescales. The Moon's influence on Earth extends beyond the tides. The Moon's gravity helps stabilize Earth's axial tilt, preventing it from varying wildly over time as it might otherwise do. Earth's axis is currently tilted 23.5 degrees relative to its orbital plane, creating our seasons. Without the Moon's stabilizing influence, this tilt could vary chaotically, causing dramatic climate changes that might make complex life difficult or impossible. The Moon is airless with no atmosphere to speak of, and dry with no liquid water on its surface, though ice has been detected in permanently shadowed craters at the poles. Surface temperatures vary from 127 degrees Celsius in direct sunlight to -173 degrees Celsius in shadow. The sky above the moon is always black, even when the sun is above the horizon and stars are visible during the lunar day. The moon's surface is heavily cratered, preserving a record of impacts spanning billions of years. The large dark areas visible from Earth, called Maria, are actually vast plains of ancient lava that erupted billions of years ago and filled enormous impact basins. The lighter-colored regions, called highlands, are older and more heavily cratered. Every feature on the moon's surface, from the smallest crater to the largest basin, tells a story about the violent history of the inner solar system. Standing on the moon and looking back at Earth, you would see a beautiful blue and white sphere hanging in the black sky, showing phases just as the moon shows phases to us. Earth would appear much larger than the moon appears from Earth, roughly 4 times larger in diameter and about 13 times larger in area. Because of the moon's synchronous rotation, Earth would remain in nearly the same position in the sky at all times, never rising or setting, slowly rotating to show different faces as Earth spins on its axis. From this lunar perspective, you would see Earth's atmosphere as a thin blue line around the planet's edge, a fragile envelope containing all the air that billions of living things depend on. You would see clouds swirling in patterns, storms forming and dissipating, continents and oceans sliding past as Earth rotates. You would see a world utterly different from the airless, waterless, lifeless moon beneath your feet, separated by less than 400,000 kilometers, yet incomparably different in character. The Earth-Moon system is unique in the inner solar system, a small rocky planet accompanied by an unusually large moon, both shaped by a violent collision in the distant past, both influencing each other through gravity and tides, together forming a stable platform where life could emerge and flourish. As we prepare to leave Earth behind and continue our journey outward through the solar system, we carry with us an appreciation for how special our home world is, how many factors align to make it habitable, and how its companion moon, born from cosmic violence, has helped maintain the stability that allowed life to thrive. Section 6. Mars, the red world of giants. Continuing outward from Earth, we cross a gap of approximately 78 million kilometers to reach the 4th planet from the Sun, Mars, the red planet. Even from Earth, Mars is distinctive, appearing as a reddish point of light in the night sky, colored by iron oxide rust on its surface. This rusty dust covers much of the planet, giving Mars its characteristic color and its ancient association with blood and war. Mars is considerably smaller than Earth, with a diameter of 6,792 kilometers, roughly half Earth's diameter and about 1/10 Earth's mass. Its lower mass means weaker gravity, about 38% of Earth's surface gravity. Someone who weighs 100 kilograms on Earth would weigh only 38 kilograms on Mars, though their mass would remain unchanged. The Martian atmosphere is thin, with surface pressure less than 1% of Earth's atmospheric pressure. Like Venus, Mars's atmosphere is primarily carbon dioxide, but unlike Venus, there is far too little of it to create a significant greenhouse effect. The thin atmosphere provides little insulation, and temperatures on Mars vary widely, from about 20 degrees Celsius near the equator on a summer afternoon to minus 125 degrees Celsius at the poles in winter. Despite its smaller size and thinner atmosphere, Mars is home to some of the most impressive geological features in the solar system. The most spectacular of these is Olympus Mons, the largest known volcano on any planet. Olympus Mons rises approximately 25 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. To truly appreciate this scale, imagine a mountain so tall that if you stood at its base, the summit would be beyond the visible horizon, hidden by the curve of the planet. But Olympus Mons is remarkable not just for its height but also for its breadth. The volcano measures approximately 600 kilometers across its base, roughly the distance from San Francisco to Los Angeles or from London to Edinburgh. The caldera, the collapsed crater at the summit itself, spans about 80 kilometers and consists of 6 overlapping collapse pits, each formed when magma chambers beneath the surface emptied and the ground above collapsed into the void. The slopes of Olympus Mons are gentle, averaging only about 5 degrees, making the volcano a shield volcano similar in shape to the volcanoes of Hawaii but vastly larger. If you were standing on the slopes of Olympus Mons, you would not see a steep mountain rising before you. Instead, you would see ground sloping gently upward, rising so gradually that the mountain's peak would be invisible far beyond the horizon. Only from orbit can you truly appreciate Olympus Mons' full size and shape. The volcano is surrounded by a cliff called the Basal Scarp, rising up to 10 kilometers high in some places, where the edge of the volcano drops precipitously to the surrounding plains. The origin of this cliff is not entirely clear, but it may have formed through landslides as the volcano's flanks collapsed under their own weight, or through erosion by glaciers if Mars once had a thicker atmosphere and more abundant ice. Olympus Mons is not alone. Mars has several other enormous volcanoes, all located in a region called Tharsis, a vast volcanic plateau that rises several kilometers above Mars's average elevation. 3 volcanoes, Arzia Mons, Pavonis Mons, and Ascraeus Mons, sit in a line across the Tharsis Plateau, each comparable in size to the largest volcanoes on Earth, though still smaller than Olympus Mons. These volcanoes grew so large because Mars lacks plate tectonics. On Earth, the crust is divided into plates that move across the surface. When a volcanic hotspot forms beneath Earth's crust, the moving plate carries the volcano away from the hotspot, and a new volcano forms above the hotspot. This creates chains of volcanoes, like the Hawaiian Islands, with older volcanoes farther from the hotspot and younger ones directly above it. On Mars, the crust appears to be a single rigid shell with no moving plates. When a volcanic hotspot forms beneath Mars's crust, the crust stays put, and lava continues to erupt in the same location for millions or billions of years. Layer upon layer of lava builds up, creating enormous shield volcanoes that dwarf anything on Earth. Olympus Mons may represent billions of years of volcanic eruptions all piling up in the same spot. Mars also features the largest canyon system in the solar system, Valles Marineris, a vast network of canyons stretching more than 4,000 kilometers along the Martian equator, about 1/4 of the planet's circumference. The canyons reach depths of up to 7 kilometers and widths of up to 200 kilometers. If Valles Marineris were on Earth, it would stretch from New York to Los Angeles. The Grand Canyon, impressive as it is, would fit comfortably into one of Valles Marineris' side channels. Valles Marineris did not form through water erosion like the Grand Canyon. Instead, it appears to be a massive crack in Mars's crust, formed when the Tharsis region rose billions of years ago, stretching and splitting the surrounding terrain. Later, landslides, wind erosion, and possibly ancient water flows widened and deepened the canyons into their current form. Evidence of water's past presence on Mars appears throughout the planet. Ancient river channels, dry lake beds, minerals that form only in the presence of water, all suggest that Mars once had liquid water on its surface, possibly in abundance. Early in its history, when Mars's atmosphere was thicker, water may have pooled in low-lying areas, creating lakes or even oceans. But as Mars's atmosphere gradually escaped into space, stripped away by the solar wind because Mars lacks the strong magnetic field that protects Earth's atmosphere, the pressure and temperature dropped until liquid water could no longer exist on the surface. Today, water on Mars exists primarily as ice. The polar ice caps contain large amounts of water ice mixed with frozen carbon dioxide, dry ice. Beneath the surface, permafrost extends across much of the planet, and high-resolution images have revealed what appear to be seasonal flows on steep slopes, possibly briny water that remains liquid despite the low temperatures because of dissolved salts. Mars has two small moons, Phobos and Deimos, both irregularly shaped and heavily cratered. These moons are much smaller than Earth's moon. Phobos, the larger of the two, measures only about 22 kilometers across, while Deimos is only about 12 kilometers across. Both moons are likely captured asteroids gravitationally snared by Mars in the distant past. Phobos orbits very close to Mars, only about 6,000 kilometers above the surface, and it orbits faster than Mars rotates. This means Phobos rises in the west and sets in the east, opposite to how moons normally appear to move. Phobos is also gradually spiraling inward, pulled down by tidal forces, and in several tens of millions of years it will either crash into Mars or break apart from tidal stresses, possibly forming a ring around the planet. More than 40 spacecraft have been sent to Mars, more than to any other planet except Earth. Orbiters have mapped the surface in exquisite detail. Landers and rovers have studied rocks and soil, searching for signs of past or present life. Mars remains a primary target for exploration because of its past habitability and its potential for future human exploration. Its proximity to Earth, its solid surface, its 24-and-a-half-hour day similar to Earth's, and its water-ice resources make it the most plausible destination for eventual human settlement beyond Earth. As we leave Mars behind, continuing our journey outward from the Sun, we depart the realm of the terrestrial planets, the small rocky worlds that orbit close to the Sun. Ahead lies a vast gap, the asteroid belt, and beyond it the domain of the giant planets, worlds of gas and ice fundamentally different in character from the rocky planets we have visited so far. Section 7. The Asteroid Belt and Ceres. Between the orbits of Mars and Jupiter lies a region of space that might seem empty at first glance, but contains millions of rocky bodies orbiting the Sun, remnants from the solar system's formation that never coalesced into a planet. This is the asteroid belt, a vast ring of debris circling the Sun between roughly 2 and 3.5 astronomical units from the Sun. Despite its name and its portrayal in science fiction, the asteroid belt is not a dense field of rocks requiring careful navigation. The asteroids are spread across an enormous volume of space. If you were traveling through the asteroid belt in a spacecraft, you would likely see nothing but empty space around you, with the nearest asteroid too distant to see without a telescope. The total mass of all asteroids combined is less than 5% of the Moon's mass. Most of this mass is concentrated in the 4 largest asteroids: Ceres, Vesta, Pallas, and Hygeia. Ceres, the largest object in the asteroid belt, is in a category of its own. With a diameter of about 940 kilometers, Ceres contains approximately 1/3 of the asteroid belt's total mass. It is large enough that gravity has pulled it into a nearly spherical shape, unlike smaller asteroids that retain irregular shapes. For these reasons, Ceres is classified as a dwarf planet, the only dwarf planet in the inner solar system. Ceres orbits the Sun at an average distance of about 2.8 astronomical units, taking 4.6 years to complete one orbit. Its rotation period is just over 9 hours, making its day much shorter than Earth's. From Ceres' surface, the Sun would appear only about 1/4 as bright as it does from Earth, a distant point of light in a black sky. Recent observations by the Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed a world more complex than expected. Ceres' surface shows a variety of features, including impact craters, smooth plains, and unusual bright spots. The most prominent bright spots, located in a crater called Okator, are deposits of sodium carbonate, a salt that may have been left behind when briny water from Ceres' interior erupted onto the surface and the water evaporated or froze. These bright spots and other evidence suggest that Ceres may have a subsurface ocean, or at least pockets of liquid water or brine beneath its icy crust. The presence of water and organic compounds detected on Ceres' surface make it an intriguing target in the search for life beyond Earth. Though any life that might exist in Ceres' dark, cold interior would necessarily be very different from the life we know on Earth's surface. Ceres' interior is thought to be differentiated, meaning it has separated into layers of different composition and density. At the center may be a rocky core surrounded by an ice-rich mantle topped by a thin rocky crust. Some scientists describe Ceres as an embryonic planet, a world that began to form into a planet but whose growth was halted probably by Jupiter's gravitational influence preventing further accretion. The asteroid belt exists where it does largely because of Jupiter. In the early solar system, material in this region began to coalesce into planetesimals, just as it did everywhere else in the solar disk. But Jupiter formed quickly and grew massive, and its powerful gravity stirred up the asteroid belt region, increasing the relative velocities of the planetesimals orbiting there. Instead of gently colliding and sticking together, these high-speed impacts shattered planetesimals apart. Over time, Jupiter's gravity also ejected many planetesimals from the region entirely, leaving behind only a small fraction of the original material. The asteroids that remain are diverse in composition. Some are metallic, composed primarily of iron and nickel, thought to be the cores of larger planetesimals that were shattered by impacts. Others are rocky, similar in composition to terrestrial planets. Still others are carbonaceous, rich in carbon compounds and water-bearing minerals, resembling primitive materials from the solar system's earliest days. These carbonaceous asteroids are dark, reflecting very little sunlight, and some contain organic molecules, carbon-based compounds that are the building blocks of life. Studying asteroids provides insights into the early solar system. Unlike planets, which have been geologically active and transformed since their formation, many asteroids have remained largely unchanged for billions of years. They preserve materials and conditions from the solar system's infancy. Meteorites that fall to Earth, fragments of asteroids knocked free by collisions, allow us to study these ancient materials in laboratories. The asteroid belt is not the only population of small bodies in the solar system. Near-Earth asteroids have orbits that bring them close to Earth's orbit. Some occasionally collide with Earth, creating meteor showers when small fragments burn up in the atmosphere, or causing significant impacts when larger bodies strike the surface. The asteroid that struck Earth 66 million years ago, ending the age of dinosaurs, was probably about 10 kilometers in diameter. Trojan asteroids share orbits with planets held in stable positions by gravitational balance between the planet and the Sun. Jupiter has particularly large populations of Trojan asteroids at 60 degrees ahead of and behind the planet in its orbit. Earth, Mars, and Neptune also have known Trojan asteroids. As we leave the asteroid belt behind and continue outward, we approach the realm of the giant planets. The next world we will encounter is vastly different from anything we have seen so far, a planet so large that all the terrestrial planets could fit inside it with room to spare. A world not of rock and metal but of hydrogen and helium. A planet that is, in many ways, more like a star that failed to ignite than like the rocky worlds of the inner solar system. Section 8. Jupiter, the majestic giant. We arrive now at Jupiter, the fifth planet from the Sun and the first of the giant planets. Jupiter dominates the outer solar system in a way that no terrestrial planet dominates the inner system. It is the largest planet in our solar system by far, with a diameter of approximately 143,000 kilometers, more than 11 times Earth's diameter. If Jupiter were hollow, more than 1,300 Earths could fit inside it. Jupiter's mass is even more impressive in comparison to other planets. It contains roughly 318 times Earth's mass and more than twice the mass of all other planets combined. Jupiter is so massive that the center of mass of the Sun-Jupiter system, the point around which both objects orbit, lies slightly outside the Sun's surface. In a sense, Jupiter and the Sun orbit each other, though the Sun's much greater mass means it moves only slightly while Jupiter traces a large orbit. Despite its enormous size, Jupiter is not made of rock and metal like the terrestrial planets. Instead, it is composed primarily of hydrogen and helium, the lightest and most abundant elements in the universe, the same elements that make up the Sun. Jupiter is, in essence, a giant ball of gas with no solid surface to stand on. If you could somehow descend into Jupiter, you would not find firm ground, only gas becoming denser and hotter with depth until it eventually transitions into liquid hydrogen. This composition makes Jupiter more similar to a star than to a terrestrial planet. Indeed, if Jupiter had been about 80 times more massive, the pressure and temperature in its core would have been high enough to ignite hydrogen fusion, and Jupiter would have become a star rather than a planet. Our solar system would then be a binary star system with two suns illuminating the planets rather than one. But Jupiter fell short of this threshold and remains a planet, though it does emit more heat than it receives from the Sun, radiating away the energy left over from its formation and from the slow gravitational contraction of its interior. Jupiter orbits the Sun at an average distance of about 5.2 astronomical units, roughly 778 million kilometers. At this distance, sunlight is only about 4% as intense as it is at Earth's distance, but this is still sufficient to illuminate Jupiter brightly. Through a telescope from Earth, Jupiter appears as a disk crossed by dark belts and bright zones, colorful bands parallel to the planet's equator created by atmospheric circulation patterns. These bands are regions of rising and falling gas in Jupiter's atmosphere. The bright zones are regions where gas rises from deeper, warmer levels, bringing ammonia ice crystals that form white clouds. The dark belts are regions where gas descends, creating gaps in the cloud layer that allow us to see deeper into the darker, warmer atmosphere below. Winds between these zones can reach speeds of up to 432 kilometers per hour, driven by heat from Jupiter's interior and by the planet's rapid rotation. Jupiter rotates faster than any other planet, spinning once on its axis in less than 10 hours. This rapid rotation causes the planet to bulge noticeably at the equator and flatten at the poles. The equatorial diameter is about 9,300 kilometers larger than the polar diameter. This fast rotation also generates powerful winds and drives the atmospheric circulation that creates the band structure. The most famous feature in Jupiter's atmosphere is the Great Red Spot, a massive anticyclonic storm, a high-pressure region where winds circulate counterclockwise in the southern hemisphere. The Great Red Spot has been observed continuously for at least 190 years, since astronomers first began keeping detailed records of Jupiter, and historical observations suggest it may be much older, possibly several centuries old. The Great Red Spot is enormous. At its widest, it spans approximately 16,000 kilometers, large enough to hold two Earths side by side. The storm extends deep into Jupiter's atmosphere, with recent measurements suggesting it may reach depths of 300 kilometers or more. Within the Great Red Spot, winds circulate at speeds up to 432 kilometers per hour, and the entire structure drifts slowly westward relative to the surrounding atmosphere. The Great Red Spot's reddish color has long puzzled scientists. The color may come from chemical reactions involving sulfur and phosphorus compounds, or from organic molecules created when sunlight breaks apart methane and ammonia molecules in the upper atmosphere. The exact chemistry remains uncertain, but the color clearly indicates that conditions in the Great Red Spot differ from the surrounding atmosphere. Curiously, the Great Red Spot appears to be shrinking. Observations from the 1800s show it was much larger then, perhaps twice its current size. The shrinking has accelerated in recent decades, and no one knows whether this trend will continue until the spot disappears or whether it will stabilize at some smaller size. Jupiter has other storms and features that come and go over timescales of years to decades, but the Great Red Spot's longevity makes it unique. Jupiter's powerful magnetic field extends far into space, creating a magnetosphere that is the largest structure in the solar system, larger than the Sun itself. This magnetic field is generated by convection of electrically conductive liquid metallic hydrogen deep in Jupiter's interior. The magnetosphere traps charged particles from the solar wind, creating intense radiation belts around the planet, far more dangerous than Earth's Van Allen belts. Any spacecraft or person venturing close to Jupiter must contend with radiation levels that would be quickly lethal without heavy shielding. Jupiter is accompanied by at least 95 known moons, with more being discovered regularly as observational techniques improve. The four largest, discovered by Galileo Galilei in 1610, are called the Galilean moons: Io, Europa, Ganymede, and Callisto. These four moons are worlds unto themselves, each unique and fascinating. Ganymede, the largest of Jupiter's moons and the largest moon in the solar system, exceeds Mercury in diameter, measuring 5,268 kilometers across. Ganymede is the only moon known to have its own magnetic field, generated by convection in a liquid iron core similar to Earth's core. Beneath Ganymede's icy surface may lie a subsurface ocean containing more water than all of Earth's oceans combined. Europa, though smaller than Ganymede, has attracted particular attention because of evidence for a global ocean beneath its smooth, icy crust. Europa's surface shows very few impact craters, indicating the surface is young, constantly renewed by geological activity. The icy surface is crisscrossed by dark lines and cracks, possibly created when tidal flexing from Jupiter's gravity fractures the ice. Where liquid water from below wells up through these cracks and freezes, it may carry with it organic molecules and possibly even microbial life from the ocean below, though this remains speculation. Io, the innermost Galilean moon, is the most volcanically active body in the solar system. Tidal forces from Jupiter and the other Galilean moons continuously squeeze and stretch Io, generating tremendous heat through friction. This heat powers hundreds of volcanoes that erupt continuously, spewing sulfur and sulfur dioxide across the surface and into space. Io's surface is constantly renewed by volcanic activity, making it the youngest surface in the solar system, with no impact craters visible at all. Callisto, the outermost Galilean moon, is heavily cratered, bearing the scars of billions of years of impacts. Unlike the other Galilean moons, Callisto shows little evidence of recent geological activity. Its ancient surface provides a window into the early solar system, preserving a record of bombardment that has been erased on more active worlds. Beyond the Galilean moons, Jupiter has many smaller moons, most of them captured asteroids or comets, irregularly shaped and orbiting in unusual, highly elliptical or retrograde orbits. Some of these small moons may be fragments of larger bodies broken apart by impacts or by tidal forces from Jupiter. Jupiter also has rings, though far fainter and less extensive than Saturn's famous ring system. Jupiter's rings are composed primarily of dust knocked off small inner moons by micrometeorite impacts. The rings are difficult to see from Earth and were not discovered until the Voyager spacecraft flew past Jupiter in 1979. As we prepare to leave Jupiter and continue outward, we can appreciate this giant world for what it represents. A planet massive enough to have shaped the entire solar system through its gravitational influence. A world where storms larger than Earth rage for centuries, where radiation belts could kill unshielded astronauts in hours, where moons large enough to be planets in their own right orbit in complex gravitational dances, where conditions are both familiar, with clouds and storms and auroras, and utterly alien with no solid surface, no breathable air, crushing pressure and searing heat in the depths. Jupiter is a giant among planets, a world that challenges our understanding and expands our appreciation of planetary diversity. Section 9. Saturn, the Ringed Wonder. Our journey continues outward to the sixth planet, Saturn, the most distant planet visible to the naked eye from Earth and arguably the most beautiful. Saturn is famous for its rings, the most extensive and spectacular ring system in the solar system, making it instantly recognizable even to those with only a passing interest in astronomy. Saturn is the second largest planet with a diameter of about 120,000 kilometers, roughly 9.5 times Earth's diameter. Only Jupiter exceeds it in size. Like Jupiter, Saturn is a gas giant composed primarily of hydrogen and helium. But Saturn is less dense than Jupiter, so much so that its average density is less than that of water. If you could find an ocean large enough, Saturn would float. This low density results from Saturn's composition and its internal structure. The planet is mostly hydrogen, with a smaller proportion of heavier elements than Jupiter has. The lower mass and pressure mean the hydrogen is less compressed, resulting in lower average density. At the center may be a small rocky core, but most of Saturn's mass is gas and liquid hydrogen. Saturn orbits the Sun at an average distance of about 9.5 astronomical units, nearly twice Jupiter's distance. At this distance, sunlight is faint, only about 1% as bright as on Earth. Saturn's year, the time to complete one orbit, is approximately 29.5 Earth years. Saturn's day, however, is short, with the planet rotating once in about 10.5 hours, only slightly slower than Jupiter. But Saturn's defining feature is its rings, a magnificent system of particles orbiting the planet in a thin disk. The rings extend outward from about 7,000 kilometers above Saturn's clouds to about 80,000 kilometers, spanning a total width of about 280,000 kilometers. Yet despite this enormous extent, the rings are astonishingly thin, in most places only about 10 to 100 meters thick. To visualize this thinness, imagine scaling Saturn's rings down to the size of a typical photograph. If the ring system were the size of a standard photograph measuring 10 inches across, the rings would be 100,000 times thinner than a sheet of paper, effectively two-dimensional. This extreme thinness results from collisions between ring particles, which gradually flatten the particle orbits into a common plane. The rings are composed primarily of water ice particles, ranging in size from tiny grains smaller than sand to chunks as large as houses. The particles are not uniformly distributed, but are organized into thousands of individual ringlets, like grooves on an old phonograph record. Some gaps in the rings, such as the Cassini division, a 4,800-kilometer wide gap between the A and B rings, are prominent enough to see through small telescopes from Earth. The rings are designated by letters in the order they were discovered, not in order from the planet outward. Starting from Saturn and moving outward, the main rings are D, C, B, A, F, G, and E. The B ring is the brightest and most massive, containing the most material. The C ring is more transparent, allowing Saturn's atmosphere to be seen through it. The F ring is narrow and complex, with braids and kinks created by the gravitational influence of small shepherd moons that orbit nearby. The age of Saturn's rings has been a subject of debate. Scientists once thought the rings were as old as Saturn itself, dating back 4.5 billion years. But recent observations by the Cassini spacecraft, which orbited Saturn from 2004 to 2017, suggest the rings may be much younger, perhaps only a few 100 million years old. This estimate comes from measurements of how much dust has contaminated the rings. The rings appear remarkably clean, composed of nearly pure water ice, suggesting they have not been exposed to dust bombardment for billions of years. If the rings are young, what created them? One possibility is that they formed when a moon or comet ventured too close to Saturn and was torn apart by tidal forces. There is a distance around every planet called the Roche limit, inside of which tidal forces from the planet's gravity exceed the self-gravity holding a moon together. Any substantial object that crosses inside the Roche limit will be pulled apart, with the debris spreading into a ring. Saturn's rings lie within Saturn's Roche limit, consistent with this formation mechanism. Another possibility is that the rings are the remains of a collision between two moons. If moons orbiting Saturn collided with sufficient speed, they could shatter, creating a debris field that would gradually spread into a ring. The relative youth of the rings, if confirmed, suggests such an event might have occurred relatively recently in solar system history. The rings interact with Saturn's moons in complex ways. Some small moons, called shepherd moons, orbit within or just outside the rings, and their gravity confines narrow rings, preventing them from spreading. Other moons create gaps in the rings. For example, the moon Mimas creates the Cassini division through an orbital resonance effect. Particles in the Cassini division orbit Saturn twice for every one orbit of Mimas, and this resonance gradually removes particles from that region. Saturn itself, like Jupiter, is a world of clouds and storms. Through telescopes, Saturn appears calmer than Jupiter, with less contrast in its cloud bands, but spacecraft observations reveal that Saturn's atmosphere is quite active. The Cassini spacecraft observed numerous storms, including occasional giant storms that erupt and spread around the entire planet. These great white spots appear once every Saturn year, roughly every 30 Earth years, though the mechanism that triggers them on such a regular schedule remains mysterious. Saturn has the fastest winds in the solar system among the giant planets, with equatorial winds reaching speeds of about 500 meters per second, nearly 1,800 kilometers per hour. These winds blow in the same direction as Saturn's rotation, unlike Earth's winds, which blow in various directions. The energy driving these winds comes primarily from heat escaping from Saturn's interior rather than from sunlight. Like Jupiter, Saturn has a powerful magnetic field and extensive magnetosphere. The magnetosphere interacts with Enceladus, one of Saturn's moons, which erupts geysers of water ice from its south polar region. These ice particles escape Enceladus and spread throughout Saturn's magnetosphere, with some eventually settling into orbit to form Saturn's faint E-ring. Saturn has at least 146 known moons, more than any other planet. The largest, Titan, is the second largest moon in the solar system, exceeded only by Jupiter's Ganymede. Titan is unique among moons in having a thick atmosphere, denser than Earth's atmosphere at the surface. This atmosphere is primarily nitrogen with some methane, and it completely obscures Titan's surface from view in visible light. Beneath its hazy atmosphere, Titan has lakes and seas of liquid methane and ethane, primarily near the poles. These are the only stable bodies of liquid on the surface of any world besides Earth. Titan has weather with clouds and rain, though the rain is liquid methane rather than water. The surface shows river channels carved by liquid methane, dried lake beds, and possibly ice volcanoes that erupt liquid water instead of molten rock. Enceladus, though much smaller than Titan, has attracted intense scientific interest because of its ice geysers. These geysers erupt from 4 parallel fractures near the moon's south pole called tiger stripes, shooting water vapor and ice particles hundreds of kilometers into space. The geysers indicate liquid water beneath Enceladus's icy surface, making it another candidate in the search for life beyond Earth. Saturn's smaller moons include many with unusual shapes and features. Some appear to be fragments of larger moons broken apart by impacts. Others may be captured asteroids or comets. Hyperion is irregularly shaped and tumbles chaotically in its orbit rather than rotating regularly. Iapetus has a bright hemisphere and a dark hemisphere, with the contrast possibly caused by dark material from another moon coating one side. As we prepare to leave Saturn behind and continue outward to the ice giants, we carry with us the image of those magnificent rings, a sight so beautiful that Galileo, upon first seeing them through his primitive telescope in 1610, though his telescope was not powerful enough to resolve them clearly, wrote of Saturn appearing to have ears or handles. When Christian Huygens observed Saturn with a better telescope in 1655, he realized the true nature of what Galileo had seen: a thin, flat ring around the planet. The rings have captivated observers ever since, a cosmic wonder that reminds us of the beauty and diversity to be found among the worlds of our solar system. Section 10. Uranus, the tilted ice giant. Traveling farther outward from the Sun, we leave behind the realm of the gas giants and enter the domain of the ice giants. At nearly twice Saturn's distance from the Sun, we arrive at Uranus, the seventh planet, a world so distant that it was unknown to ancient astronomers and was discovered only in 1781 by William Herschel. Uranus is the third largest planet with a diameter of roughly 51,118 kilometers, about 4 times Earth's diameter. It is significantly smaller than Jupiter and Saturn, but much larger than Earth. Unlike the gas giants, which are mostly hydrogen and helium, Uranus is classified as an ice giant because its interior contains large amounts of water, methane, and ammonia ices in addition to hydrogen and helium. These ices are not necessarily frozen solid given the high pressures and temperatures inside the planet. Instead, they exist as hot, dense fluids. Uranus orbits the Sun at an average distance of approximately 19 astronomical units, about 2.8 billion kilometers from the Sun. At this distance, sunlight is 400 times fainter than on Earth. Uranus takes 84 Earth years to complete one orbit, a human lifetime almost exactly. Anyone born when Uranus was at a particular point in its orbit would be approximately 84 years old when Uranus returned to that same point. The most striking feature of Uranus is its axial tilt. While most planets have axial tilts of less than 30 degrees, Uranus is tilted 98 degrees. This means Uranus essentially rotates on its side, with its rotation axis nearly in the plane of its orbit around the Sun. Imagine Earth tilted so that the North Pole pointed almost directly at the Sun in June and the South Pole pointed at the Sun in December, and you have some sense of Uranus's orientation. This extreme tilt creates unusual seasonal patterns. For about 1/4 of Uranus's 84-year orbit, one of its poles points almost directly at the Sun, experiencing continuous sunlight while the opposite pole remains in darkness. 42 years later, the situation reverses, with the previously dark pole now in continuous sunlight and the previously sunlit pole now in darkness. Between these extremes, the planet goes through periods when the Sun appears to rise and set as seen from most latitudes. The cause of Uranus's extreme tilt remains uncertain. The most widely accepted hypothesis is that Uranus was struck by a very large object, perhaps an Earth-sized planet or several large planetesimals early in its history. Such collisions were common in the early solar system, and a sufficiently large impact at the right angle could have knocked Uranus onto its side. Alternatively, gravitational interactions with other giant planets during a period of orbital migration might have gradually tilted Uranus, though this would require a very specific set of circumstances. Uranus's magnetic field adds another layer of peculiarity. Unlike most planets where the magnetic field axis aligns reasonably well with the rotation axis, Uranus's magnetic field is tilted 59 degrees from its rotation axis. The magnetic field also does not pass through the planet's center but is offset. This unusual magnetic field configuration suggests that the field is not generated in the planet's core, but in a sloshing layer of electrically conductive ice and water in the outer part of the interior. Uranus appears as a pale blue-green disk when viewed through telescopes. This color comes from methane in the planet's upper atmosphere. Methane absorbs red light and reflects blue and green light, giving Uranus its distinctive color. The atmosphere is quite bland compared to Jupiter and Saturn, showing few features in visible light. This may be because Uranus emits very little heat from its interior, less than any other giant planet relative to the sunlight it receives. Without internal heat to drive convection and atmospheric motion, the weather on Uranus is less vigorous than on the other giants. However, observations with advanced telescopes and during Uranus's equinoxes, when the sun shines on the planet's equator rather than on a pole, have revealed that Uranus does have weather. Storms appear as bright spots in the atmosphere, and wind speeds can reach up to 900 kilometers per hour, or 560 miles per hour. These winds blow primarily in the same direction as the planet's rotation, forming bands parallel to the equator, though these bands are far less distinct than Jupiter's or Saturn's. Uranus has a faint ring system discovered in 1977 when astronomers observed Uranus passing in front of a star, and noticed the starlight dimming before and after Uranus itself blocked the star. These dimmings revealed the presence of narrow rings around the planet. The rings are composed of dark particles, possibly organic compounds or radiation-processed ices, making them much darker and harder to see than Saturn's bright, icy rings. Uranus has 27 known moons, named after characters from the works of William Shakespeare and Alexander Pope rather than mythological figures like most other planetary moons. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. These moons are composed of roughly equal parts ice and rock and show a variety of surface features. Miranda, the smallest of the 5 major moons, has one of the most unusual surfaces in the solar system. It shows a bizarre patchwork of different terrains, with some regions heavily cratered and ancient-looking, while other regions show enormous cliffs and complex grooved terrain. One cliff on Miranda rises about 20 kilometers, more than twice the height of Mount Everest. Scientists are still not entirely certain what created Miranda's strange appearance, though possibilities include a massive impact that partially disrupted the moon, or tidal heating that caused geological activity in the past. Only one spacecraft has visited Uranus, Voyager 2, which flew past the planet in January 1986. During its brief encounter, Voyager 2 discovered 10 new moons, confirmed the ring system, measured the magnetic field, and took the only close-up photographs we have of Uranus and its moons. The images revealed a remarkably featureless planet with just a few faint clouds. Though, as mentioned, later observations from Earth have shown that Uranus has more atmospheric activity than the Voyager images suggested. When Voyager 2 flew past, Uranus's south pole was pointed almost directly at the Sun, so Voyager 2 essentially looked down on the southern hemisphere. The northern hemisphere was in complete darkness and could not be photographed. Now, decades later, Uranus has moved far enough in its orbit that both hemispheres receive sunlight, and observations have revealed differences between the two hemispheres, with more storms appearing near the poles as they emerge from decades of darkness. Uranus rotates relatively quickly despite its large size, taking about 17 hours and 14 minutes to complete one rotation. This rotation, combined with the planet's sideways orientation, means that the direction of sunrise and sunset depends on where you are on the planet and where Uranus is in its orbit. At the poles, the sun would appear to spiral around the horizon during the periods when that pole is neither in full sunlight nor full darkness, creating unique lighting conditions unlike anywhere else in the solar system. As we prepare to leave Uranus and journey to the outermost planet, we reflect on this tilted world, a planet knocked askew by some ancient catastrophe, spinning sideways through space, experiencing seasons unlike any other planet, with a magnetic field that points in an unexpected direction, wrapped in a bland blue-green atmosphere that occasionally erupts in storms, orbited by moons with names from literature rather than mythology. Uranus reminds us that even among the giants, each world has its own character, its own quirks that set it apart from all others. Section 11. Neptune, the windiest world. Our journey through the solar system brings us now to the eighth and final planet, Neptune, the most distant of the major planets, orbiting in the cold, dim outer reaches of the Sun's domain. Neptune was not discovered through systematic searching of the sky, but through mathematics. When astronomers noticed that Uranus's orbit deviated slightly from predictions, they hypothesized that another planet beyond Uranus was gravitationally perturbing its orbit. Calculations by Urbain Le Verrier in France and John Couch Adams in England independently predicted where this unknown planet should be. And when Johann Galle searched that region of sky in September 1846, he found Neptune within a degree of the predicted position. Neptune is slightly smaller than Uranus, with a diameter of about 49,500 kilometers. But it is more massive, containing about 17 times Earth's mass compared to Uranus's 14 Earth masses. Like Uranus, Neptune is classified as an ice giant, with an interior containing large amounts of water, methane, and ammonia, in addition to hydrogen and helium. The two planets are similar enough in size and composition to be considered twins, yet they differ in significant ways. Neptune orbits the Sun at an average distance of 30 astronomical units, about 4.5 billion kilometers. At this vast distance, the Sun appears as merely a bright point of light, only about 1/900th as bright as it appears from Earth. Neptune takes approximately 165 Earth years to complete one orbit. It was discovered in 1846 and completed its first observed orbit since discovery only in 2011. Anyone born when Neptune was discovered would need to live to 165 years old to see it return to the same position. Despite receiving so little sunlight, Neptune shows more atmospheric activity than Uranus. This activity is powered by heat from Neptune's interior. Unlike Uranus, which emits barely any internal heat, Neptune radiates about 2.6 times as much energy as it receives from the Sun. This internal heat drives convection in the atmosphere, creating winds and storms that make Neptune a surprisingly dynamic world. Neptune holds the record for the fastest winds in the solar system. Wind speeds have been measured at up to 2,400 kilometers per hour, roughly 9 times stronger than the strongest winds on Earth. These supersonic winds blow primarily in the opposite direction from Neptune's rotation, a retrograde pattern quite different from the wind patterns on the other giant planets. The mechanism that accelerates these winds to such extreme speeds remains not fully understood, though it clearly involves the heat rising from Neptune's interior. Through telescopes, Neptune appears as a deep blue disk, even more intensely blue than Uranus. This color also comes from methane in the atmosphere, but Neptune's deeper blue suggests additional unknown chromophores, substances that absorb red light may be present. The atmosphere shows distinct features, including dark spots that appear and disappear over timescales of months to years. When Voyager 2 flew past Neptune in August 1989, It observed a large dark spot in Neptune's southern hemisphere, dubbed the Great Dark Spot, similar in relative size and position to Jupiter's Great Red Spot. This was a high-pressure system with winds of up to 2,400 kilometers per hour circulating around its edges. But when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had disappeared, replaced by new dark spots in other locations. Neptune's storms are more transient than Jupiter's Great Red Spot, forming and dissipating on timescales of years rather than centuries. Neptune has a magnetic field similar in strength to Uranus's field, and like Uranus, the field is tilted significantly from the rotation axis and offset from the planet's center. The tilt is 47 degrees, not quite as extreme as Uranus's 59-degree tilt, but still highly unusual. This similarity between Uranus and Neptune suggests that tilted, offset magnetic fields may be a common feature of ice giant planets, possibly related to how the fields are generated in slushy layers rather than in solid cores. Neptune rotates in about 16 hours and 7 minutes, slightly faster than Uranus despite being slightly smaller. This rotation, combined with the planet's internal heat and the resulting atmospheric dynamics, creates the complex wind patterns and storm systems that make Neptune the most meteorologically active of the ice giants. Neptune has a faint ring system discovered during stellar occultation, similar to how Uranus's rings were discovered. Neptune's rings are dark and tenuous, with some rings showing clumpy arcs rather than being uniform around the planet. These arcs are thought to be maintained by gravitational interactions with small moons embedded in or near the rings. Neptune has 14 known moons, the largest of which is Triton, discovered just 17 days after Neptune itself was found. Triton is unusual in several respects. With a diameter of 2,700 kilometers, it is the seventh largest moon in the solar system and the largest moon orbiting in a retrograde direction, opposite to its planet's rotation. This retrograde orbit strongly suggests that Triton did not form alongside Neptune but was captured by Neptune's gravity, possibly from the Kuiper Belt. Triton has a thin atmosphere of nitrogen with traces of methane. The surface temperature is about -235 degrees Celsius, cold enough that nitrogen freezes into ice. Despite this extreme cold, Triton is geologically active. When Voyager 2 flew past, it observed geysers erupting from Triton's surface, shooting nitrogen gas and dark particles 8 kilometers into the thin atmosphere. These cryovolcanic geysers may be driven by seasonal heating of nitrogen ice beneath the surface or by tidal heating from Neptune, though Triton's current orbit is too circular for strong tidal heating. Triton's retrograde orbit is gradually decaying. Tidal forces are slowly drawing Triton closer to Neptune, and in several billion years, Triton will cross inside Neptune's Roche limit and be torn apart by tidal forces, creating a spectacular ring system around Neptune, possibly more extensive than Saturn's current rings. Neptune's other moons are much smaller than Triton. Proteus, the second largest, is only about 420 kilometers across and has an irregular shape. Most of Neptune's moons are small captured objects, though some of the inner moons may be fragments of larger moons destroyed by impacts or tidal forces. Like Uranus, Neptune has been visited by only one spacecraft, Voyager 2, which flew past in 1989. This single flyby provided most of our detailed knowledge about Neptune and its moons. Everything we have learned since then has come from Earth-based telescopes and the Hubble Space Telescope, which have continued to monitor Neptune's changing atmosphere and discover additional small moons. Neptune marks the edge of the realm of major planets, the boundary between the bright, warm inner solar system where planets orbit the sun in decades or less, and the dark, cold outer solar system where objects take centuries to complete their orbits. Beyond Neptune lies a vast region populated by icy bodies, remnants from the solar system's formation that never coalesced into planets, a frigid frontier that extends outward for billions of kilometers before the sun's influence fades and interstellar space begins. As we prepare to leave Neptune behind and venture into this outer realm, we carry with us an appreciation for this distant blue world, a planet discovered through mathematical prediction rather than direct observation. A world of extreme winds and transient storms despite receiving so little energy from the distant sun. A world orbited by a large captured moon spiraling slowly inward to its eventual destruction. A world that reminds us that even at the edges of our solar system, far from the sun's warmth and light, planetary processes continue. Weather happens, moons erupt geysers, and the universe remains active and dynamic. Section 12. The Kuiper Belt and Beyond. Beyond the orbit of Neptune, in the cold, dim outer reaches of the solar system lies a vast region populated by countless small icy bodies. This is the Kuiper Belt, named after astronomer Gerard Kuiper, who predicted its existence, a disc-shaped region extending from roughly 30 astronomical units, Neptune's distance, outward to about 50 astronomical units from the Sun. The Kuiper Belt is similar in some ways to the asteroid belt between Mars and Jupiter, but much larger and containing far more objects. While the asteroid belt consists primarily of rocky and metallic bodies, Kuiper Belt objects are composed largely of frozen volatiles, ices of water, methane, ammonia, and other compounds that remain frozen at the extremely low temperatures prevailing so far from the Sun. Estimates suggest the Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers across, and billions of smaller objects. These are remnants from the solar system's formation, planetesimals that never accumulated into a planet, preserved in deep freeze for 4.5 billion years. They represent pristine samples of the material from which the outer planets formed, offering clues about the early solar system's composition and conditions. The most famous resident of the Kuiper Belt is Pluto, discovered in 1930 by Clyde Tombaugh, and considered the solar system's 9th planet for 76 years. Pluto is a world of modest size with a diameter of about 2,377 kilometers, smaller than Earth's moon. Its orbit is elliptical and inclined, tilted 17 degrees relative to the plane where most planets orbit. At times, Pluto ventures inside Neptune's orbit, though the two objects will never collide because of orbital resonances that keep them apart. Pluto orbits the Sun at an average distance of about 39 astronomical units, taking 248 years to complete one orbit. At this distance, the Sun appears merely as a bright star, providing only 1/1600th the light that Earth receives. Noon on Pluto resembles twilight on Earth, a dim illumination that barely distinguishes day from night. The surface temperature on Pluto averages about -230 degrees Celsius, cold enough that nitrogen, which is a gas in Earth's atmosphere, freezes into ice on Pluto. In fact, much of Pluto's surface is covered with nitrogen ice, along with frozen methane and carbon monoxide. Pluto has a thin atmosphere, but it freezes and falls as snow onto the surface when Pluto is farthest from the Sun in its orbit, then sublimates back into gas when Pluto approaches closer to the Sun. In July 2015, NASA's New Horizons spacecraft flew past Pluto, providing humanity's first close-up views of this distant world. The images revealed a surprisingly complex and geologically young surface. One region, informally named Sputnik Planitia, is a smooth plain of nitrogen ice apparently no more than 10 million years old, with convection cells suggesting the ice slowly circulates. Mountains of water ice rise several kilometers high. Long valleys and ridges cross the surface. Reddish organic compounds called tholins, created when ultraviolet light breaks apart methane molecules, color some regions a rusty red. Pluto has 5 known moons, The largest, Charon, is about half Pluto's diameter, making the Pluto-Charon system almost a binary planet. Charon orbits Pluto in just over 6 days, and Pluto rotates at the same rate, so the two bodies are tidally locked to each other. From Pluto's surface, Charon would appear to hang motionless in one place in the sky, never rising or setting. The 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are tiny, irregular bodies probably captured from the Kuiper Belt or formed from debris of an ancient impact. In 2006, the International Astronomical Union redefined the term planet to require that a planet must have cleared its orbit of other objects. Pluto, sharing its orbital region with many other Kuiper Belt objects, did not meet this criterion and was reclassified as a dwarf planet. This decision was controversial and remains debated, but it reflected the discovery of many Pluto-like objects in the outer solar system, some comparable to or larger than Pluto. One such object is Eris, discovered in 2005, which is slightly smaller than Pluto in diameter but more massive. Eris orbits much farther out, at an average distance of about 68 astronomical units, in a highly elliptical and inclined orbit. Other large Kuiper Belt objects include Makemake and Haumea, both classified as dwarf planets, and Sedna, which orbits even farther out in what may be a distinct inner Oort cloud population. Kuiper Belt objects show a variety of colors, from gray to reddish to surprisingly bright. Some, like Pluto, have high albedos, reflecting 50% or more of the sunlight that strikes them. Others are dark, reflecting only about 10%, similar to the Moon's albedo. These color and brightness variations reflect differences in composition and surface processing by radiation. Many Kuiper Belt objects are in orbital resonances with Neptune, meaning their orbital periods are simple ratios of Neptune's period. Objects that orbit twice for every 3 Neptune orbits, called Plutinos because Pluto is among them, are particularly common. These resonances protect the objects from close encounters with Neptune that might eject them from the solar system. Some Kuiper Belt objects have been perturbed into orbits that bring them into the inner solar system. These become comets, spectacular visitors that grow bright tails as sunlight vaporizes their ices. The short-period comets, those with orbital periods less than 200 years, originate primarily from the Kuiper Belt. When a Kuiper Belt object is gravitationally scattered inward, perhaps by an interaction with Neptune, it may end up on an orbit that brings it close to the Sun, where solar heating causes its ices to sublimate. A comet consists of a nucleus, a solid body typically a few kilometers across, composed of ice and rock. When far from the Sun, a comet nucleus is inactive, just a dark, cold lump. But as it approaches the inner solar system, sunlight warms the surface and ices begin to sublimate, turning directly from solid to gas without becoming liquid. The escaping gas carries dust particles with it, creating a cloud around the nucleus called the coma, which can grow to hundreds of thousands of kilometers across. The solar wind and solar radiation pressure push the gas and dust outward, away from the Sun, creating tails. Comets typically have 2 tails. A dust tail, yellowish and curved, composed of dust particles reflecting sunlight, and an ion tail, bluish and straight, composed of ionized gas molecules accelerated by the solar wind. The tails always point away from the Sun regardless of the comet's direction of motion. So as a comet recedes from the Sun after perihelion, it travels tail first. Beyond the Kuiper Belt, from about 50 to perhaps several thousand astronomical units, may lie the Oort cloud, a spherical shell of icy bodies surrounding the solar system. The Oort cloud has never been directly observed because its objects are too small and distant, but its existence is inferred from the orbits of long-period comets, those with orbital periods of thousands or millions of years. These comets approach from random directions rather than from the plane where planets orbit, suggesting they originate from a spherical distribution. The Oort cloud may contain trillions of icy bodies with a total mass several times Earth's mass. These objects are so weakly bound by the sun's gravity that passing stars can gravitationally disturb them, occasionally nudging objects into orbits that bring them into the inner solar system as long-period comets. The Oort cloud marks the true edge of the solar system, the region where the sun's gravitational influence finally gives way to the gravitational effects of nearby stars. Somewhere in this outer darkness, the solar wind slows and merges with the interstellar medium, the thin gas between the stars. The boundary where this occurs is called the heliopause, and it lies at about 120 astronomical units from the Sun in the direction of the Sun's motion through space. Voyager 1 crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018. These spacecraft, launched in 1977, continue to transmit data from beyond the solar system, more than 45 years after launch, traveling outward at speeds of about 3.5 astronomical units per year. The region beyond Neptune is a realm of darkness and cold, where temperatures hover only a few dozen degrees above absolute zero, where the sun provides no appreciable warmth, only faint illumination. Yet even here, worlds exist, diverse in their compositions and characteristics, preserving information about the solar system's birth, occasionally sending comets sunward to dazzle observers on Earth, slowly orbiting the distant sun in periods measured in centuries, remnants of a time when the solar system was young and still forming. As our journey through the solar system draws to a close, we have traveled from the sun outward across billions of kilometers, visiting 8 major planets, 5 dwarf planets, hundreds of moons, millions of asteroids and Kuiper Belt objects, and countless comets. We have seen worlds of rock and worlds of gas, worlds of ice and worlds of iron, worlds with thick atmospheres and worlds with no air at all, worlds with volcanoes and worlds with ice geysers, worlds with rings and worlds with massive storms, worlds baked to melting temperatures and worlds frozen nearly to absolute zero. Each world tells its own story, shaped by its distance from the sun, its size and composition, its orbital characteristics, its geological activity, its interactions with other objects. Together, these worlds form a system, a family of objects born from the same molecular cloud, shaped by gravity and collision, migration and resonance, still evolving even now, billions of years after their formation. Our solar system is both our home and our classroom, teaching us about planetary processes, atmospheric dynamics, geological evolution, and the conditions necessary for life. It is a diverse collection of worlds, each worth studying, each adding to our understanding of how planetary systems form and evolve. As you drift towards sleep, let these images linger in your mind. The ancient sun, burning steadily at the center of everything. Swift Mercury with its long, strange days. Venus shrouded in sulfuric clouds, crushing and hot. Earth and its moon born from collision, unique and precious. Mars with its giant volcanoes sleeping beneath rusty skies. The asteroid belt, remnants of a planet that never formed. Jupiter, majestic and massive, its great red spots swirling for centuries. Saturn with its impossibly thin, impossibly beautiful rings. Uranus tilted on its side, rolling around the sun. Neptune distant and blue with the fastest winds in the solar system. And beyond, the Kuiper Belt and the edge of the sun's domain, where Pluto and countless icy bodies slowly orbit in the darkness and cold. These worlds are real. They exist right now, orbiting the sun just as they have for billions of years, just as they will for billions more. This is our solar system, our cosmic neighborhood, revealed through centuries of patient observation and decades of spacecraft exploration, a testament to human curiosity and ingenuity. If you enjoyed this journey through the solar system, please consider liking this video and subscribing to Nighttime Science for more relaxing explorations of science and the natural world. Rest well, and clear skies to you.